streaming and shit. Sorry for the black screen. I'm doing shit and shit. Okay, I have my stream up here. Okay. We're building the Colosseum. I'm actually going to, let's see. Can I like add something to here? Maybe like this. I have the camera. Okay, I'm gonna arrange my camera properly. I got this thing for Christmas. Whoa. It's pretty epic. What did you say? I'm gonna be careful, like, not to give away, like, dox myself or something. So that's like #1 priority right now. Not dox myself. So I'm gonna actually take off my jacket because I should be fine now. I think everything's working. We have flat surface here. Everything should be fine. Hands. Surface to build Lego. Nothing that could dox me or anything. No important information. Shit, we got like 2 viewers and that's pretty cool. I'm gonna pop out the chat. Actually, I don't need it yet. I have chat right there. I'm just like getting everything up and like running and stuff. I think we are basically good to go, besides just me moving my chair. Okay, sorry for like the loud noise right now. I gotta like open up the nice. Lots of stuff going on right now. It's like all off screen. Yeah, pizza. Like the, I'm not even sure you guys can hear me. Can you guys hear me? Oh, I think you can. The backbone calling me on UBS. Oh, some moves are. Oh wow, there's a miniature box in here. Okay. Ugh. These things are long. And you guys can see we got like 4 of like these box moves. See what we need for the first bag. First bag, I need like a bunch of these things. All kind of these. Sorry if you guys can't see me. I have like stuff happening. 2, 3. 4, 5, 6. I can look at a trash can. Yeah, I'm gonna go get like a trash can. I mean, like a trash bag, so I can put all this all, like the extra bags. So I'll be right back. Okay, I'm back. Sorry to keep y'all waiting. Got trash bags. We have 6 there. 7, 8. 9. Gotta get one more. Ah. Okay, I'm gonna arrange these real quick. I got 4 viewers on a Lego building stream. That's pretty cool. This is a cool little technique you can do. Like how to can I peel them off easily. So, and stream like isn't that bad. Which is nice. You should be careful doing this in like smaller pieces. You know, and actually smush them together, and then you can't take them apart. So. Okay. There's that big giant part that's in the front of my desk for later. Now the bag of 1. Hell yeah. 1, 2, 3, 1. This. Bags. Okay, I am in now on a chair. You guys like come? Come? Is that pretty cool? Okay, I am going to pull up. Oh wait, that's probably copyrighted music. Let's pull up my cool playlist. Playlist. Vibe with no lyrics. I hope. The desktop audio won't overpower everything else. Okay. I guess we start building now. Oh, this is too loud. Okay, here we go. I have extra Lego pieces on my desk for a build I'm working on. Let's push those away. God, there's so many Legos over here. I'm gonna have to go against everything that I usually do and put these together. One big massive pile. Wait, important. Wait, I should probably pull up my VS. Oh shit, I muted the desktop audio. Look, important. Okay, I'm gonna put these ones up here because they're like tiny and shit. Falling off. Oh god. I have so little room in my desk. Here we go. Okay, so grab two of these and put them together. Wait, I didn't put it on loop and shit. Well. Okay, next page. Let me do it once. Do these. Do these. Oh, I put them on the wrong side. Oops. The 4 people watching, Merry Christmas. Yeah. Okay, there we go. 8 now. Ooh. Actually, I should probably point my camera more towards me, where I'm doing all like the building and stuff. Yeah, it's like my long flowing locks of hair. God, these big pieces are quite interesting. God, I can barely see anything. Bend it in weird ways. 7 of these. Whoa. Okay, so 2 go here. 2 go here. Oh shit, and we do that on this 2 times, but flipped. Okay. Okay, then we connect it to. Connect it to. Hello? Here, give me a second. I'm mute. Sorry about that. My mom came in and talked to me. So I just mute this just in case. Alright, so now we have this thing. Let me put more. Da-da-da-da. Oh, I didn't hear the click. Dum, 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 dum. Can you connect these? Dang, I'm not hearing the satisfying little clicky sounds that these little like stud things make. Oh, I only got one viewer now? How sad. Oh, well. I guess I put this over here now. And another one pops off. And you connect to the big guy. God, I didn't realize how massive this thing is until like just now. This is like less than half of it. Wow. I have nowhere like to put this thing. Shit. Okay, I have now experienced a worriness of where to put this thing now. Of like building it on my desk or whatever. Okay, I have a plan. I'm gonna move my mouse over to here. I'm gonna move my phone and then my like keyboard to like here. So now I have space where like my mouse and stuff is, so I can like properly do shit. So I can like build. Still not enough room. Thinking. Okay, I think that should do. I moved my keyboard up a whole lot. Sorry, I think I should have enough room now. Hopefully. I pray. Okay, anyways. Keep building. Oh, this thing's too bright. Oh, but it's bad for the camera. If I just move like right here. Yeah, that'll work. Oh yeah. Two of these. One of these. And 1x3. And 8 of these. 1, 2, 3, 4, 5, 6, 7, 8. You guys see me alright? Move that more there. Or something. That's good? Hopefully this. You see my shitty posture when I'm messing with Legos. I like the song. God, this thing is so massive. Stick. God, it's gonna be like hanging off over this edge. Luckily, the main portion is going to be in the middle, so the heaviest section. Oh, I only need one of these. Oh. All the buildings gonna be on this side. Actually, I'm gonna move my camera more towards like here, so you can see stuff that's happening like all over the place. I should do. Really pull up this here. So we have like stuff happening here, building that's happening here. I think that'll do. Should work. Here, I'll move my mouse so I can see stuff better. Yeah, I think that'll work. My closet right there. Trash bag. Right there. Yeah, I think that'll do. Stick. Going. Oh, we got things. 1x8s. 1, 2, 3, 4, 5, 6. Yeah, 1x8s. 2 1x8. Stick. Stay down. Right. Oh, 1 1x3. 3 of these. Oh, 2. 1 by what is these? 10s? Probably 10. And then 6 of these. 2, 3, 4, 5, 6, and then 3, 4, 5, 6, and 7, 8. You can barely even fit on like the page and like the instructions. It's kind of funny. Got 4 viewers again. That's pretty cool. Actually, can y'all even see like what I'm doing? That's like build in like a way y'all can see, or is that okay with y'all if I like build like this? I'm gonna build like this until like someone says something. Actually, I'm gonna build like this until someone says something. It's just easier for me. It's cool how the person who designed this did like color coding. It's pretty neat. I think it's mirrored for the most part on this side because I can't see what's happening on that side. Just I'm like blind to it just because it's like printed off of it. Hey, we hit 5 viewers at one point. It's pretty cool. Watch me like have missed it ×2 at like the beginning. No, 1, 2, 3, 4, 5. Oh, I'm gonna check. Please don't tell me I did. That'd be pretty dumb. Okay, I didn't. That's pretty good. Onto the bottom part. This way. Got some of these. 2 of these. And one goes there. Okay. Did I do this wrong? Yeah, that's fun enough. It's like went wrong somewhere. Oh, I found it. Put the song wrong. Nah. The headset's gonna fall off. Fit. God damn it. There you go. Actually, you know what? I am going to go and put on a hat because, like, my hair is just like everywhere. Yes, it's my brand image. It's the may all your memes be Danecat. My brand image. I have too much fucking hair. Like an awkward mirror. Okay, that should work. I think this is fun. Okay, now I think I did this right. Yeah, that looks better. 3 of these. Watch these tiny ones. Those 2x4s. They're tiny now, even though 2x4s are usually a medium. My bad. Sorry if I hurt any of y'all's ears. Okay, looks like I got all of them. What are these for? What? They're like, they're just there. Mm-hmm. 48 of these? Holy macaroni. Wait. Did I miss a ×2? Oh shit, I think I did. Because I still have an entire extra half of bag 1. Oh shit, I think I do. I didn't see a ×2 though. Oh no. Shit, there's a ×2. Oh, okay then. I guess, we have to do this thing twice. That didn't make a lot of sense. Well, okay then. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I don't need to count anymore. I have so many of these. Oh. Alright, that's 46. I thought I said 48. And the final 3 of this thing. Okay. Oh, 1/2 is done. Look at this. Guess we have to do a thing where we go all the way back to the beginning. Yay! Okay, let's back. There's like not enough room to do like anything with this. Oh, fuck. Move more stuff. Make more room. My mouse again. Okay, half of it is now right here, and it is now over the half of the desk, so I should be fine. I sure hope so. Okay. Please. That's a really nice sound. Okay. I really like that sound. Oh, that sounds so good. There's the time too. I missed it. I'm so smart. Fit together. There we go. Ow. My fingers. Oh hey, it's been inside of one another. That's kinda cool. Like this. A cheek. Hey, I got the perfect amount. That's pretty cool. Sure, up to this, right? Yeah, I did. Oh wait, it's this thing. I'm not working the big one anymore. Put this thing backwards. Oh no. Yo, what am I doing? My brain hurts. Like this. Yes. That wasn't as good as this one. Oh yeah, I got my braces off. I have a beautiful smile now. Time to spend the rest of the holiday working on this thing. I like that sound. And put it together. Eh. Monkey. What? These last two don't wanna. There we go. There we go. Everything's all nice together. Hey, look, we're on top of each other. How am I doing that? What? 1, 2, 3, 4, 5, 6, 7, 8. Right. Almost tripped. God, my back feels weird. I always, whenever I build Legos, I'm like, Legos. But like, I need to like relax. I'll have bad posture. I'll be like an old person with a cane, always on the back, like, oh, I'm old, you know? Yes. Ow. Ow. God, my viewer fluctuation is like all over the place. It's like, here, I can show you. Let's look at this. Oh, I see my screen now. Oh, it's all over the place. So, and then pretty neat. So I'm back. Legos. I haven't shift like almost 3/4 of an hour. Huh? I haven't heard any other songs in a while. Upside down. Ugh. Alright, I forgot to put the top stuff on. Do later. One, a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Probably shouldn't put it on that page. That's the page I need. It's so big. Like throw it or something. Nope. Also, the edge of the stand, right? Push this back a little bit, maybe. Down, maybe. Huh? Would you like your pizza? There you go, pizza. Did I do this backwards? Oh, I did. Did it wrong. Oopsie, oopsie. Bum 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 ba 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 ba. Yeah. And then back to the top. Feet dexterity for the win. I feel like I did something wrong. I missed a... Cause I have two extras. Two extra of each one's. Little Technic pieces. And... That's from what I can remember, I haven't built a Lego set in a while, but from what I can remember that's abnormal, but... I ended up getting an extra piece in the Lego set I built a couple days ago. I mean, a family Lego set, but... I haven't had any big ones like these in a while. The last one I had was the Harry Potter Castle thing, Hogwarts thing. So I like the big ones just because like they're fun. Oh, I got a message. Use password. Sorry for not doing stuff right now. Sister wanted to talk to me real quick. Oh. Hello. Hello, family. Oh. And last four. 1, 2, 3, 4. Ta-da! And then they go like God, I don't know how to do this. I only have so many hands. That. There goes. I'm not supposed to put these together yet. Okay. Now we move on to number 2. So let's go do that now. Oh God. Ever. Spin chair. I don't know why I did that. Back to putting these pieces on. Yay. So many of them. I hate the repetitive tasks in Legos. Just putting the same piece on it like 5,000 times. It's quite boring. But you know, gotta do it. You gotta do what you gotta do. Okay, so my goal for the stream is to get through that first little mini box that I had. So get through 1/4 of this build. I mean, not 1/4, but one box. I mean, it's close to 1/4, but amount of pieces wise, it's like a 16th or something. Oop. So I'm gonna take all of the ones from this part. Why did they put them in 2 separate bags? That doesn't make any sense. Nope. That one fell off. Yeah. Oh, there it goes to the ground. Oh, I feel it. Hell yeah. Toe dexterity for the win again. I think I should be holding this up. Prevent these ones from falling off. Built like this. Cool. Presentation or a sign you're holding up. Come look at my thing. Yeah. Oh no. Where'd that one go? There it is. Pick it up. Finger dexterity. Yes. I mean toe dexterity, my bad. Wait a second. Lost one. Where'd it go? Did I place one wrong, or did I lose it? Oh, this is not good. Off the search. I'm actually not going to put my headphones on for this since it's going to be easier to not have the headphones. So, you guys can enjoy some nice music. Yes. Chat, but I guess I'll 3 to place, but 1 extra. I mean, you either need to have an extra, you gotta place one. Put that there. Didn't. Okay. This just doesn't actually use that these like almost never extras. I mean, they are never extras. No, I don't extra. It's just weird. Well, let me guess this step. That's song. Oh no, we're still on a what is it, the Mist song. Okay, finished these. God, this thing is massive. Holy macaroni! There it is. Sorry for the loud noise. It'll be funny. I'm doing this because it's funny. Oh, I know I did something. I have the cam mini stream. Mini stream. Mini stream. Mini stream. Mini stream. Make it bigger. There. Mini stream. Mini stream. I see. Settings stream. Let's change the bitrate. Can I not change it midstream? Tools. I guess I can't change it midstream. Well, I guess we're stuck with, what is this? 8,000 bitrate? Stream! Mini stream! Move this up a little bit. Mini stream! Turn down my volume. Mini stream! Okay, you guys can tell me if you don't want it. I thought it'd be funny. Grab myself. I'm gonna punch myself. Wait, punch. I wanna punch myself, it'd be funny. Ow. Wait, does that even work? Oh wait, no, I have to be like, wait, no. Ow. Okay, and then wait for that to happen or something. It seems like I saw like a long time. Shit, I'm like standing still in the stream. What am I doing? I should be building. I have to be funny, mess myself. Oh wait, it's about to happen. No, wait. Oh wait, that's wrong. Pow. I'm so bad. I'm still punching. Also, this means you all can see the stream delay in the top corner right here. Cause I'll be like, wave, and then y'all can see when I wave in the mini stream and see how big the stream delay is. That's pretty cool. Anyways. Ow! My nails are, I should cut my nails again. Nails are so long and I keep on like stabbing the like underside of my nails because like they're so like soft. It hurts. Don't fit. Do something. Yeah. They got connected. That's pretty cool. I'm gonna watch the stream, see if I threw one of the pieces on accident. It looks like I just did. No, I didn't. Alright. Even if I did, I have extras. I have like a whole like big Lego thing back there. So search there in case I'm missing a piece. I've only ever had one missing piece in a Lego set, which is quite good after the mass amount of Legos that I have. So good job, Lego. Funny enough, it was like one of the pieces that I didn't have at the time. So it was a 1x6 in this turquoise color, or this like red, maroon, red, or whatever. Not turquoise. Turquoise is wrong word. Stick, go. Heck. Hey, an extra one again. What? What the fuck? Oh. God, Legos have to be so strong sometimes. Pardon. Mini stream. I don't know why I find that so funny. I just do. Okay. We are almost done. Just put this thing on here with the bag, the two. Oh, I found it where it goes, where this missing one went. Boom. Alright. On to back 3. Yeah. And I put them together at the very end of this. Yes. By the way, I'm planning on using this song as my stream intro, and I have permission. It's pretty cool. I have my armrest. Ooh. You know what? I am going to go get myself something like drink or something, maybe eat. I'll be back in a bit. You guys can watch the mini stream and the stream. So, yeah. I'll do a little. So I can repeat really fun. Okay, that was only like 2 loops that was gone. I got myself a Sprite. So, now I like that. Pretty funny seeing myself just come back. No, yeah. Oh, I'm back. Oh, cool. Oh, hey, I'm back again. That's pretty cool. Anyways. Tasty. Oh, big things now. 2 of these, 2 of these. Actually, 4 of these since we're doing it on each side. Big block, big. And 4 of these. Wait, no, we need like a lot more of these. Oh wait, no, we only need 2 of these. These go on the side of it. Oh, wiggly. Gotta be careful. Yeah, it's gonna be even if like throughout the entire thing until we move on to the next bag or something. And hey, I have a singular like. How epic. I'll slowly grow my channel. How many subs do we have now? Got my keywords all the way up here. I have 77. Went down one, like since like a day ago. And I don't really care too much. I mean, like, oh, ka-chow. But like, I don't really care too much. I just think it's cool to see myself grow. So that's the only reason why I look at the sub count, really, and like likes and stuff. See how I'm growing since 0 sub me. It'd be pretty epic to hit a mill, like before I go to college, but chances of that are extremely low. I'm looking more towards maybe hitting like a 1K by the end of right before I go to college, and then 100 by the end of next year. So nope. My fingernails like chipping away. Wait, something real quick. Feels like streaming or something. Feels like. Oh shit! I actually. Black 2x4s. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, Where'd it go? One, two, three, four, 5, 6, 7, 8, 9, 10, 11. Cool. Alright. Two. 1, 2. Four. There we go. And 1, 2. Here we go. Legos. 1, 2. 1, 2. Big. It's like break like super often. I have like 10 of these. Or, maybe not 10, like a lot of these, and most of them are just broken. They're so chunky. Four, 5, 6, 7, 8. two of these, 1, 2, 3, 4. Two of these, so 1, 2, 3, 4. 1, 2, 3, 4. No. Well, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I got 10 of these now. Wow, that's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Then grab 2 of these. Another 2 of them. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, something just fell. I'm gonna put these on and see if I can find what fell. Yep, something definitely fell. Search time. Uh-oh. Definitely just no wrong. One, two, three, four. 1, 2, 3, 4. Aha, I see what I did wrong. Wait, what? Did something very wrong. Oh, stop that. Here. Here. Yeah. Okay, there we go. Like this. And like this. And then like this. Okay, so I messed up like everywhere. Okay, there we go. Rearrange everything, and then here it is. Big ending. These two halves together. Oh my god. How? It's so difficult. I'm gonna take this off for a bit. I'm getting there. I'm doing something. Oh. No. Hell yeah. Hell yeah. Jeez. What's the piece count? Give me a sec. Gotta pull up the big box, boy. What's on the instructions? It doesn't say Justin, but it's like the third largest set. I'll do a little research. Colosseum Lego set. Piece. It has almost 10,000. It's close to 9,000. But yes, it has 9,000. Are you watching your stream on stream? Yeah! Top left corner. Hell yeah. Why wouldn't I? Okay. Time to set to build the thing there. Okay, so I think I move it more to this way. Actually, let's see. Like that. You all can see this is where I'm gonna be doing the most of the building. Keep on frequency. Up, oopsies. Oh yeah, I'll see it. Hey, come back. Shit. I can like fall asleep on this thing. Yeah. Manage my chair. Oh yeah. Even though my keyboard already has an numpad, I got another one, so I could organize my Minecraft inventory faster. You know, just like, and then boom. Instead of having to go like, and then do it on the other one that's over here. Go like, you know, only big brain. Only big brains. Here. Bum, 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 bum. Wait. Long. I do 2 times. You know what I'm gonna do? Oh, left a piece in here. Okay. This is something that I also really like to do. I'm gonna put a link in the description of. Let's just make this big. Put a link in the description for this. But I am no longer gonna be listening to this. We're gonna pull up C real quick. SEA. C. I'm gonna link his channel below because I don't wanna like copyrighted by him or anything. Okay, save that. And we're gonna be listening to his fucking Giga Brains. Shuffle.
Did you know that if you stand atop the Shard, the tallest building in London, you can look southwards and see France on a clear day? When the air is clear, it would appear to be empty and transparent, but air is far from empty.
Hell yeah, C is
Right
super
now,
good.
the air
Good.
around you contains
I really
approximately
like him.
10 trillion atoms per cubic meter. That's a lot of atoms.
Okay, hope this is not too loud for him.
Emptier, you have to go higher.
DMCA'd.
Above Earth's surface,
The, so a politician is trying to pass a law that says you could basically you could go to jail for
which is the space between star systems.
Yeah, you could basically go to jail for not proper
travel even further and go to the space between galaxies.
I don't say you can go to jail for copyrighted music or just copyrighted things, and it's actually because the music industry, all the music companies, right? What they're doing is they're giving the politician like a bunch of money. Charlie or Critical, he made a video on this. You can go check it out.
These filaments group into concentrated areas called galaxy superclusters. When viewed
That's
on a
super
wide
funny.
scale, they all sort of connect. But what about the
C's a really good channel, by the way. I really recommend y'all to go look at his channel.
Well, these spaces are just about as remote and empty as you can get in the universe, and we have a fitting name for them: voids. We
Actually,
are
I'm gonna turn this up.
fascinated by other galaxies and what could exist elsewhere that we often overlook the significance of the voids in between. They are a component of the universe itself, and they've taught us a great deal about areas ranging from galaxy superstructure formation to
Okay, I
the
hope it isn't too loud.
universe itself.
Politics stream?
Today, we're going
No.
to revisit some of that knowledge.
Politics, stay out of my channel for the most part, unless it's something that's like really stupid, like this DMCA thing.
The contents of the macro universe could be broken down into 2 structural components: walls, where matter exists in abundance, and voids, the space in between. A void is a vast, somewhat spherical region of space with a low cosmic density. We measure cosmic density by physical galaxy counts as opposed to estimations of mass, so the technical definition for a void references an area with a low number of galaxies, approximately 1/10 of the typical number inside walls, according to the widely accepted definition. Whereas galaxy walls are composed of gravitationally bound structures and filaments, voids are not technically structures. They are the vast spaces between the structures, but are nonetheless a fundamental property of the universe. Voids can exist both inside galactic walls and in the spaces between them. The smallest are about 10 megaparsecs in diameter, with a megaparsec being equal to roughly 3.2 million light years, meaning typical voids are usually at least 30 million light years wide. Larger typical voids can reach up to 10 times that size, giving them a whopping diameter of around 300 million light years, or 100 megaparsecs. And at that size, we have another name for them, supervoids. But they can get even larger still. Voids which form inside galaxy walls are smaller than voids that form in the low density spaces of the universe. These empty spaces can be much bigger, with some of the largest areas we've found over 1 billion light years in diameter. It's hard to appreciate just how large that scale is. There's no absolute ratio for the share of galaxy walls and voids in the universe, but what we do know is that the vast majority of its volume is made up of these massive near-empty spaces of low cosmic density. Cosmic voids became a branch of study in astrophysics in the 1970s, when redshift surveys became more common. By the end of the decade, voids had been identified in the foreground of the Coma cluster and the A1367 cluster. Redshift surveying technologies have come a long way since then, and it wasn't long before we were mapping our universe in exquisite 3D detail for the first time. By the 1990s, 3D redshift surveys, such as the Las Campanas survey, were identifying and confirming an abundance of voids throughout the observable universe, and today we have catalogued hundreds of them. Our nearest is the local void, which starts at the edge of our local galactic group and extends over 200 million light years into the darkness. Voids have existed for as long as the universe. This is because during the first trillionth of a second of time, our universe was tiny and its contents was under unimaginable pressure. Within this ultra-dense primordial soup, quantum fluctuations were causing ripples, and then the universe suddenly expanded violently in an event known as cosmic inflation, and went from microscopic to immeasurable. Like a snapshot of the tiny universe, the contents of the universe as it was in that moment was radically elongated, and the tiny acoustic ripples now propagated across massive cosmic distances, leading to the universe's early plasma, from which the first particles formed, being more concentrated in certain areas and less dense in others. Within the dense areas, structure formation began to occur. First, dark matter began pulling together into massive but diffuse filaments over hundreds of millions of years. And then, baryonic matter traced its path. Subatomic particles became atoms, and atoms became gas clouds, and clouds became stars. The stars collected into groups which formed the first galaxies, and the galaxies moved into clusters, which became superclusters. The scale really is incredible. These structures now interlink to form a massive, sponge-like path over the entire universe.
Okay, so I have to go like eat food. So I'm gonna do a funny, okay? I'm just gonna keep this thing. Keep this. It'll be funny. It'll be funny, I promise. Like I'm gonna wait for it to loop back. Okay. Bye, I guess. The resolution. Oh my god. Oh my god. Oh, that was beautiful. I returned to this absolute like shit stain. Oh, that was beautiful. That was beautiful. Anyways, let's go back
The
to the
cosmic web. As all of this took place, the areas of lower density from cosmic inflation were emptied out, and now exist as massive voids between galaxy walls. For this reason, those massive primordial spaces between walls really are empty.
Oh, my message.
Hundreds of millions of light years devoid of not just normal matter, but dark matter
The
as well.
box.
It all grouped together in filaments in the early universe and cleared out incomprehensible gaps in the space in between. We don't really know how big these voids can get, and new discoveries continue to push the benchmarks.
Wait, today's Sunday?
In contrast, voids which occur inside galaxy walls form as gravitationally bound galaxies are pulled towards one another, which empties out the surrounding space as they converge. The more galaxies merge, the stronger their overall influence, which attracts more galaxies, and so this process is
Yes.
self-reinforcing. This leads to denser clusters and emptier voids. And in fact, when voids form like this, if two form relatively close to each other, a snowball-like effect can lead to something remarkable. While supervoids may be somewhat of a less glamorous area of astronomy, one which has continued to attract particular online attention is the Great Boötes Void, which lies on the edge of the Hercules supercluster. This void is enormous, estimated to be between 250 million and 330 million light years in diameter and over 200,000 cubic megaparsecs in volume. Upon its discovery, scientists disputed whether there had been enough time since galaxy structures began forming to allow a void of this size to exist. But as it turns out, the Boötes void isn't actually that unusual or unexpected, and the key to understanding why is hidden in the distribution of a few dozen galaxies within. 60 isolated galaxies exist within the void where thousands would usually be expected, and they make up a tube-like formation near the centre. Scientists now think that this tube may be what's left of the boundaries of two smaller voids, which merged as they grew into one another. The near-perfect spherical shape of the void is the result of a soap bubble-like effect as they merged, and two large voids combined into one massive void, leaving the galaxies on the edge of each stranded inside this new supermassive cosmic abyss. In addition to its size, the Boötes void is also thought to be one of the sparsest and most eerily empty of its kind. To put the 60 galaxies into some sort of perspective, it's like driving from coast to coast of the United States and passing only a couple of towns on your way, and this doesn't even take into account that the void is three-dimensional. As such, it's earned itself the nickname the Great Nothing, which has been puzzling astronomers since its discovery in 1981. It's so enormous that even light takes hundreds of millions of years to reach the galaxy's inside, and for light leaving the galaxies to reach the outside. In fact, astronomer Greg Aldering at the University of Minnesota said that if humanity had evolved on a world within one of these few dozen central galaxies, we wouldn't have known that other galaxies existed until the 1960s. Imagine scientists in the 60s trying to work that one out. Another thing that voids have helped us to slightly better understand is the mechanism of dark energy, the big unknown force which is pushing the universe apart and speeding up its expansion as it goes. Dark energy expands the universe in all places at once, and not just at the edges. Every part in space grows at the same rate. This means that the swathes of empty space inside the voids of the universe are also growing, pushing the edges outwards, causing them to increase in size as the universe ages. Because we now know that the size, shape and evolution of large voids is partly due to the expanding space within, we can use them to test our current estimations of dark energy's abundance. The simultaneous existence of the largest voids we see in the universe
I don't
today
have this one in.
is about 70% of the universe's energy density to be dark energy, a figure which is relatively consistent with our measures of the cosmic microwave background,
There you
which
go.
is a good sign from a research standpoint at least. Another thing we can use the cosmic microwave background for is measuring baryonic acoustic oscillation patterns, aka the distribution of normal matter and energy across the universe. On this map, the warmer areas correlate to filaments and the cooler areas correlate to voids and supervoids. All of this aligns with and reaffirms our current understanding, except in one place.
Oh, I should probably show you guys the map that he showed.
In the early 2000s, an area of the CMB which was
Here's like the
unusually
map.
cold in
That's how it looks
comparison
like.
to its surrounding areas was identified in the direction of the constellation of Eridanus. It's not the temperature of the area itself that's so unusual, but the difference in temperature between it and the relatively warm ring around it. The temperature deviates by about 70 microkelvin, whereas mean temperature variations are usually just under 20 microkelvin or so. And in some places, the temperature varies by as much as 140 microkelvin. This was a puzzling discovery, but it quickly became a big mystery of astrophysics in 2013, when the Planck satellite also detected the cold spot, ruling out any chance of it being a WMAP error. This thing actually exists somewhere out there, but what is it? Well, a group of scientists came out and proposed that a supervoid could in fact be responsible. If this hypothetical Eridanus supervoid exists, then it is probably at least 500 million light years in diameter, and could be as large as 1 billion light years, totally dwarfing even the Boötes void. There is no concrete explanation for the cold spot as of yet, and different studies since then have found conflicting results pertaining to the supervoid hypothesis, but nothing really substantial for or against it yet. And so, while it may not be a supervoid, for now at least, the cold spot is yet another perplexing and fascinating mystery of our universe. Okay, so enough theories and hypotheses. How about a real example of a mind-blowing void which has significance to us? Well, this is where the elasticity of the term void comes into play. Obviously, when you think of a void, you think of a massive, virtually empty area, like the Boötes void, or a completely empty gap between galaxy walls. However, because the term refers to a lower than expected number of galaxies, voids can contain clusters and even superclusters of galaxies and still have this apparent underdensity. As it so happens, the largest known void in the universe contains such galactic structures, the largest void which you happen to be sat in the middle of right now.
Shit.
It might sound crazy, but the KBC void is the largest known void by definition in the entire observable universe, with a lower than expected concentration of galaxies across a roughly spherical expanse of nearly, wait for it, 2 billion light years. And yet, it contains you and I, the planet, the galaxy, the local galactic group, and even a large chunk of the Laniakea supercluster, which is home to no less than 100,000 galaxies. So it's not that exciting when you think about it really, but what is interesting is that we are fairly close to the centre, relatively speaking. While this position doesn't have any implications for our existence that we know of, it does have implications for our observations of the universe around us. Our position in comparison to the rest of the universe is like living in a remote rural town instead of a city. The cities are gigantic galactic walls. Because these cities and galaxies are denser than us, they are exerting a gravitational influence on us, pulling us through the void and towards the filaments very slowly. This movement may actually be interfering with our measurements of redshift values, and has probably led to some inaccurate estimations in our calculations of the Hubble constant, our measure of the rate at which the universe is expanding. This might explain
we have one more
analyzing redshift values of galaxies around us.
One more bag and I'm gonna end the stream.
Is different to the figure we get from analyzing the CMB, which would mean that analyzing the cosmic microwave background, or echo of the Big Bang, is a more accurate means to study the expansion of the universe, from our perspective at least. If anything, the KBC void shows us that not all voids really live up to the image of one. We are simply situated in a less dense region of space, like being out in the intergalactic countryside of the universe. The only noticeable side effect this has for us is that our night sky is a bit darker than it might be on planets within galaxy walls, but it's certainly a lot less creepy than it would be if we were in the centre of, say, the Boötes void. Just imagine what it would be like in one of its isolated galaxies within.
Oh.
In the future, when the universe is so large that all other galaxies have receded from view, everywhere that isn't gravitationally bound will expand into its own massive, isolated pocket of the universe, leaving unfathomably large voids in the space in between.
Missing one of these.
Galaxy. And in the distant future, when entropy reaches maximum, no structures
Don't
will
know
remain,
where it could be.
making the universe one indescribably enormous cosmic void. Huge swathes of emptiness in space are a natural property of the
I guess I'll
universe,
just build
which always have
through
been
it
and always
until
will
I
be.
find
But just because they're
it.
empty doesn't mean they can't be interesting.
But that might be a missing piece, sadly. Unless it's like hiding behind a piece somewhere. Doesn't look like it though. Looks like I might be missing one. Missing a piece. Not super good, but it's okay.
There are hundreds of sextillions of stars in the universe, and while the Milky Way contains an estimated 400 billion of those stars, that's still a comparatively minuscule sample size. This incomprehensible expanse means we will never know for sure just how big the biggest star in the universe really is. The overwhelming majority of stars are simply too far away for us to ever be able to measure. That being said, we have discovered no shortage of giants within our own backyard, stars that dwarf our sun, and some that could even swallow up most of our own solar system. Increasingly accurate estimations of size and distance mean that the league table for the list of the largest stars is ever changing, but if we look for the largest star discovered to date, we come to the magnificent
Scooty.
Discovered in the 1800s but reclassified as the largest star at the start of this decade, Scooty has some absolutely insane numbers associated with it. And today, we are going to be taking a look at this Titan's profile, history, possibilities for exoplanets, and how the beast may reach the end of its life pretty soon.
Definitely looks like I'm missing a piece. I'm gonna do a little bit of looking around in the area that I'm in.
Scooty is a red-hot giant pulsating variable star located roughly 5,100 light years from the Earth in the constellation of Scutum. The star sits in a similar area of the sky to Sagittarius A, the engine black hole at the centre of the Milky Way, in a fairly central galactic location. At just over 7 astronomical units in diameter, this gives the star a radius of a massive 1,700 times that of our Sun. However, despite this massive disparity in size, we predict its mass to be between only 7 to 10 times that of our Sun, and is nowhere near the record for the most massive star ever discovered. This is because star size and star mass don't correlate in a linear fashion, but then again, we don't have a lot in the neighbouring regions to compare it to, so it is quite difficult to estimate the star's mass. Speaking of neighbouring regions, Scooty is believed to be extremely luminous, as you might expect given the size, 400,000 times brighter than the Sun perhaps. However, it is not visible to the naked eye and does not appear that bright in the night sky due to the star's position within the Cygnus Rift, an area within the Milky Way that is obstructed by its dark bands of dust and gas. Furthermore, Scooty is also close to the zone of avoidance, an area of the night sky we can't really observe because the Milky Way's bright galactic plane obstructs it from our perspective. Given this luminosity, you would expect Scooty to be one of the hottest stars out there, but that isn't the case either. In fact, quite the opposite. Its surface temperature is estimated to be just under 3,000 Kelvin. In comparison, the Sun's surface temperature is almost double this, at 5,778 Kelvin. Just as it doesn't correlate to mass, size does not always correlate to temperature. This is because stars that are this enormous in size are almost always no longer in their main sequence. The main part of the star's life when the hydrogen fuel the star was created with is being fused in the core. When this hydrogen in the core runs out, heavier elements such as helium are fused, but hydrogen continues being fused on the outer layers of the core. When this occurs, the outward pressure of the radiation generated is much greater than the immense pressure of the star's own gravity, which causes the star to expand and balloon to hundreds of times larger than it was during the main sequence. This is how UY Scuti and the vast majority of other red giants and red supergiants came to be so large.
And this
but
is
it
a
also
bit,
means
all
that
I,
it is
all I know that I
entirely
have are
dangerous alive.
lighter versions
Given
of
that
it.
the star is out of its main sequence, you'd expect it to be at
Honestly,
least
I have
8 billion
no
years
idea
old.
what to do.
But this post-production phase
I
doesn't
have
actually
zero clue
provide
what to
us
do.
with much insight as to how old the star is. It could be
This
billions
is
of
not
years
good.
old, but because it's so large and ejecting a lot of its mass, this instability could be indicative that the star
I guess I can
is
just keep on building and see if
and is just an inefficient
somehow it
star
shows
with a
up.
short lifespan. While this
Really
instability
doubt it
doesn't tell
will,
us
though.
how long it's been around for, what it does tell us is that it hasn't got long left to live, on a cosmological timescale anyway.
It's not.
As we mentioned earlier, this star
Very
is the
cool.
largest known star in the
I'm gonna go look
galaxy.
in another spot that I
Its
think might
radius
be.
is approximately 1,700 times larger than the Sun's. So how do we put this in some kind of perspective? Well, for starters, this impressive volume means that you could fit our Sun into the star 5.1 billion times. Photons travelling at the speed of light would take about 14.5 seconds to circle the circumference of our Sun, but for UY Scuti, it would take light the best part of 7 hours. That is 7 hours travelling at the fastest speed in the universe. Were you to fly something around it at a more human speed, say if you flew a standard Boeing 777 aeroplane around the surface at its normal operating speed, it would take well over 1,200 years to circle it just once. You may have already heard this stat, but to place UY Scuti at the centre of our solar system, its 7 astronomical unit xmas diameter would engulf everything as far out as the orbit of the Sun.
Oh, lucky me.
82 moons and the
Got
asteroid
an extra.
all consumed by this one star.
That's pretty cool.
While we can't estimate UY Scuti's mass very accurately, we know it appears to be ejecting a lot of its mass following the advent of the dying stage of its life. It is losing mass at a rate of about 5.8 times 10 to the negative 5 solar masses per year, so that's 0.000058 of a solar mass. This seems insignificant, but in tons, a solar mass is 2 with 27 zeros after it. So while this amount is not catastrophic when spread out over the entire surface, it is still ejecting millions of trillions of tons of solar radiation every year, and much more than the average star. This gives it a considerable extrasolar surrounding of dust and gas, and is yet another indication that this beast is going to go supernova in the not too distant future. For a star so far away and obscured by so many variable factors, we actually know quite a lot about UY Scuti. Our fascination with the enormous has led us to tirelessly adapt and refine our techniques of star observation and cataloguing. But it hasn't always been this way. So the question is, how did the star's profile begin? UY Scuti was first noted over 150 years ago, when German astronomers at the Bonn Observatory recorded it in a survey in 1860.
No.
As you may be aware, most stars are named after the survey or catalogue they are recorded through, such as Messier objects, Kepler objects, the Henry Draper catalogue, and the list goes on. UY Scuti was no exception. It was noted during the Bonner Dirk Musterung Stellar Catalogue survey, and was declared the 5,055th star between 12 and 13 degrees south, as it was originally coined BD 125055. But in the years that followed, the brightness appeared to have changed when it was surveyed again, leading to the discovery that the star was actually a variable star, more specifically a pulsating variable star. Pulsating variable stars come in many different forms, but generally they are a type of star that changes their luminosity and relative size due to the expansion and contraction of layers on the surface of the star. Variable stars are invaluable to astrophysicists. It's through them that we learn a lot more about the interior processes of a star. Main sequence stars, such as our Sun, tend to be more stable, with outward pressure and inward pressure from gravity counteracted in a relatively stable equilibrium. But variable stars pulsate and vary based on the rate of radiation escaping from the core and outer shell layers of the star. As there is an international protocol for recording variable stars, BD 125055 was reclassified and became the 38th variable star in the constellation of Scuti. It was then renamed UY Scuti accordingly, the title we know it by today. The rate that UY Scuti pulses is considered irregular, but it seems to have a pulsation period of about 740 days roughly. a little over 2 calendar years on Earth. Because there is so much obscuring the star, we didn't actually know about its enormous size until fairly recently. It wasn't until 2012 when UY Scuti's size was re-estimated to be about 1,700 solar radii, placing it firmly above the former largest known star, Canis Majoris. While we're almost certain that UY Scuti is the largest star we've ever discovered, it is far from definitive. Obstruction from light within the Milky Way is just one of the difficulties we face when taking measurements. UY Scuti's distance from Earth is a contributing factor. Because of its surrounding area, we can't get wholly accurate data on how far away it is, and it becomes difficult to then deduce its size. As mentioned, the former largest star was VY Canis Majoris, and was a fairly well-known star among the scientific community. While estimates of its size also had well-defined margins of error, we have managed to refine the estimates down considerably in recent years. Initial estimates when it was first discovered put the star at over 3,000 times larger than the diameter of the Sun, but this has since been re-examined, and the boundary now sits between 1,420 solar radii to 2,000 solar radii, which is still quite a big margin. The 2,000 solar radii estimation is probably a bit optimistic, and so it's likely that Canis Majoris is much nearer the 1,500 solar radii mark. In comparison, UY Scuti's radius is estimated to be approximately 1,708 solar radii, give or take 192. This means that even at its lower bound estimate, it is still in excess of 1,500 times the size of the Sun, and most likely the larger of the two red hypergiants. There are a few other stars that sit in the league table between Canis Majoris and UY Scuti, but the estimates of their size are considered much less reliable. When comparing stars, we always rank based on the lower bound estimate. So for example, Canis Majoris is classified as 1,420 solar radii, which probably doesn't do it justice. A star larger than that, perhaps, is WOH G64, a star within the Large Magellanic Cloud, a satellite galaxy at the edge of the Milky Way. Its parameters are uncertain, and sits between 1,500 times the size of the Sun and 2,500 times respectively, which would make it the largest star ever discovered. Unfortunately, it is surrounded by a thick envelope of dust and is much further away than most stars we analyse, so until technology improves, this boundary doesn't look set to narrow anytime soon. Something slightly closer to home is Westerland 126, a star with very strong radio emissions, but again has very vague estimates of its size
What was that?
with a difference in upper and lower bound of over 1,000 solar radii. Something maybe only a fraction larger
I don't know what fell off.
is HD 143183, a red supergiant
Have a
with
look.
much more precise estimations, perhaps just under 1,500 solar radii, a very similar size to the star. And then finally, there are two stars from RSGC1, a young star cluster within the Milky Way, which are estimated to be also just under 1,500 solar radii. But UY Scuti, of course, still takes the grand prize as the largest known star, for now at least. But one thing to consider is, if it is the largest, what implications does that have for its chances of supporting life?
Find it. It goes.
Like most stars, UY Scuti may have a planetary system orbiting it, but in this case we will likely never be able to observe it due to its low apparent visual magnitude and its sheer size. We detect planetary systems orbiting stars by detecting small dips in brightness, which can be indicative of a planet passing in front of the star and blocking a small fraction of the light. The problem with UY Scuti is that it is so enormous that even if a planet did pass in front of it, it would be far too small and insignificant to be detectable. These small variations in magnitude would be completely distorted by the pulsing and fluctuations in brightness of the star too. Furthermore, matter is constantly being ejected out of the star at a somewhat
There you go.
significant rate.
Good on.
Given its size and the massive amounts of stellar radiation this would equate to, the possibility
Let's
of
flip this thing over.
having its
Oh,
own
no.
planetary system is statistically unlikely. But
Two of
if it were to
these,
sustain a human-like
two of
civilization
these.
there, how far away would a planet need to orbit to be in its habitation zone? Well, we sit at 1 astronomical unit away from the Sun, approximately 150 million kilometers. For UY Scuti, the habitation zone is more likely to be about 1.5 trillion kilometers away, about 1,000 astronomical units, meaning light and heat reaching the planet will take around a month to travel the distance. This also means that in order to complete a full calendar year on the planet, you would need about 10,000 years to orbit the star just once. This means that the planet's seasons, as we know them at least, would last 2,500 years each. Entire civilizations would likely exist never knowing any other season than the one they were born out of. We're talking such vast amounts of time that any intelligent civilizations probably wouldn't even see them as seasons, but rather natural climate change. If the star ever supported life at any point, no matter what form it took, the odds suggest that this would have been at some point during the main sequence. Now, this star is far too volatile and ejects far too much radiation to give life a realistic chance of evolving. And there's also something else. UY Scuti is only expected to burn for another 1 million years. Its ejection of mass is a sign that it's reaching the end of its life. Stars outside of the main sequence burn for a fraction of the time they do during the main stage because they are ejecting their outer layers and becoming less stable. All of the hydrogen fuel in the core UY Scuti was formed with has been used up, and the star is now fusing heavier elements, turning them into oxygen and carbon. However, this process will continue, and eventually the helium will be all fused up, and the process will reach a physically unsustainable point. It is thought
There you
that
go.
UY Scuti could evolve into another stage before it goes supernova, either into a
On
yellow
to number
or
5.
a much more luminous blue hypergiant, or to what is known as a wolf red star. Whatever it evolves into, all three eventualities will create strong stellar winds that will expose the core, and will mark the beginning of the end. Based on its location within the Milky Way galaxy, we know UY Scuti to be a metal-rich star, and so eventually the core will begin to fuse iron. When it does this, no heavier elements can be produced, and the outward radiation, which once caused it to expand to this incredible size, will no longer be able to balance its own gravity, causing the star's outer layers to
hours,
collapse
so.
into an extreme supernova. Except, because of its size, this won't just be a supernova, it will be a more appropriately named hypernova. It will explode with the power of over 100 supernova explosions, emitting high amounts of gamma radiation, which will decimate any planetary system around it. Thankfully, Earth will be much more affected, and it isn't likely to be a million years is a pretty short time span on a statistical timescale. Following the explosion, if UY Scuti had evolved into a wolf red star beforehand, then the gases dispersed by the supernova could act as incubators for new stars following its death, like a phoenix rising from the ashes. The amount of mass lost in the hypernova will determine what becomes of the leftover dead core. If what remains intact exceeds 4 times the mass of the sun, then it will likely collapse in on itself to form a black hole. But if not, it will form a neutron star. UY Scuti is not particularly massive, as we mentioned earlier. If it loses the majority share of its mass, it will probably not be massive enough to become a terrifying black hole you would typically expect from such a huge star. UY Scuti is a giant of creation, but only within the abridged sample size of the Milky Way galaxy that we have to observe. With 2 trillion galaxies out there, and trillions more beyond the boundary of the observable universe, it seems a bit presumptuous to assume that UY Scuti is the biggest star in the universe, as some refer to it as. But here's an exciting thought. Say humanity does manage to colonize the Milky Way galaxy. If we can survive approximately 3.5 billion years into the future, then we will probably be around to witness the collision of the Milky Way and Andromeda. When this happens, our nearest neighbour is due to bring almost 1 trillion new stars with it to bolster our galactic family. And with this new compound galaxy containing nearly 3 times the amount of stars we have currently, imagine what other record-breaking stars we are likely to find. But that's a long way off in the future, and there are plenty of scientific barriers to cross before then. In the meantime, thank you very much for watching, and don't forget to keep reaching for the stars. Have you ever heard of dark matter? You probably have. I mean, it's a fairly common term in astrophysics. But do you know what it is exactly? And as a bonus question, what about dark energy? Well, as it happens, these may be trick questions. Dark matter and dark energy are two fascinating and elusive concepts of astrophysics, but even a top scientist would have a much easier time explaining what the phenomena are not as opposed to what they are. Both terms are quite aptly named after the ambiguity that surrounds them, and both refer to the unknown. These unknowns represent giant gaps in our knowledge of the cosmos, colossal mysteries that are waiting to be unravelled and solved. We have made some truly remarkable astronomical breakthroughs in recent decades, from mapping the afterglow of the Big Bang to emulating superclusters of millions of galaxies with pinpoint precision, to the more recent breakthrough that was imaging a supermassive black hole from 55 million light years away. Science marches on, but the next hurdle is solving the two tricksters of cosmology, dark matter and dark energy. The advent for humanity is fast approaching to start embracing dark physics, and so that's what we're going to be looking at today. In as graspable an overview as possible, what is dark matter, what is dark energy, and what are their implications for the universe. Let's first start with the easier of the two. Dark matter is a term given to a hypothetical form of matter, expected to be unlike anything discovered before. It is believed to be non-baryonic, meaning it doesn't follow the standard structure of most matter, i.e. electrons and neutrinos, and this might mean that dark matter may constitute some kind of undiscovered subatomic particle. Obviously, we have our periodic table of elements, and have a fundamental understanding of a myriad of different types of atomic and molecular structures, but dark matter could be the remaining blank, the type of particle we have yet to discover. One thing to note is that the use of the word dark is somewhat inaccurate, and a term such as invisible matter or unknown matter might be slightly more scientific. This is because dark matter does not appear to interact with observable electromagnetic radiation, and as such, it is invisible to the electromagnetic spectrum. In layman's terms, it doesn't emit or reflect light, and so it appears to be invisible from Earth. This means that it cannot be picked up using standard astronomical equipment either, and so studying it is exceedingly difficult. But despite being so elusive, dark matter is expected to account for up to 85% of the matter of the observable universe, and a little over a quarter of
I'm
its
breaking.
density. These figures stem from the apparent commonality of dark matter, which is hypothesized to be so due to its observed gravitational effects on galaxies, which cannot be explained by observable matter alone. If that was hard to follow, basically, the matter that we can see in the universe, stars, galaxies, black holes, etc., is simply not enough matter to explain some of the astronomical phenomena we have observed. A large part of the cosmic jigsaw appears to be missing, and we'll look at why that is in a second. But chiefly, experts believe that dark matter is both common and frequently occurring throughout the known universe, and plays a key role in its structure and evolution. Oh, and before I go any further, it's also worth mentioning that dark matter is not what you see in black holes. The two are entirely different. Dark matter was first hypothesized when astronomers noted an apparent lack of matter in the universe. It began in 1884 when William Thomson, aka Lord Kelvin, theorized that the total mass of the Milky Way might be larger than the mass of all the visible stars, and supposed that the large majority of stars in the galaxy were what he described as, quote, dark bodies, structures that we cannot observe but still exist and have mass. While some distance from what we now know to be the truth, this idea was explored in greater detail by Henry Poincaré, who coined the term matière obscure, which translates to dark matter, and I'm sorry if I'm butchering the pronunciation of both the name and the term. Fast forward 40 years, and astronomer Jacobus Kapteyn proposed the existence of an unknown type of matter in 1922. This was also explored by Jan Oort a decade later, who suggested that the mass of the Milky Way must be greater than what we can see for the stellar motions we have observed to occur. A year later, Fritz Zwicky was studying the Coma Galaxy cluster and theorized that its total mass had to be at least 400 times greater than the expected mass of the matter that was visible for the fast orbit that had been observed to occur, and the source of this mass was nowhere to be seen. As it happens, Zwicky's ratio estimations were extremely overrated, but he did correctly assume one thing: the majority of the universe's matter must be this invisible, undiscovered matter. In the 1980s, Astronomers Kent Ford and Vera Rubin
My back hurts.
published a paper arguing that galaxies must contain at least 6 times their observable mass in order to maintain their shape without ejecting mass as they rotate. In 2006, the crucial breakthrough was made when scientists were able to confirm the existence of dark matter when they assessed displaced stars and gas amid a collision of 2 galaxy clusters. This didn't explain what dark matter was, but did help us to understand a little more about how it impacts on gravity in superstructures. But enough about its history. What is the actual evidence for its existence? Well, there are 3 main lines of evidence for dark matter. The first is the rotation of galaxies. If the matter we could see in galaxies, mainly stars and nebulae, was the only matter present, then the motion of a galaxy's spin would quickly eject most of its stars. Yet the hundreds of billions of galaxies we have observed remain intact. By taking Kepler's law and the solar system's structure into account, we can conclude that galaxies must be much denser and more massive on their outskirts, with said mass binding them from the outside. This load-bearing invisible mass is believed to be dark matter. The next evidence comes from galaxy clusters. Our solar system isn't a wide enough area to analyse dark matter in our own galaxy, but galaxy clusters are so massive that they provide observation angles wide enough that we can study dark matter in a number of ways. If we simply estimate the mass of all the visible matter within a cluster, we can then analyse the behaviour of the clusters and reverse engineer how massive they actually must be to exhibit such behaviour, and then we can compare and contrast the 2 figures to get a sense of how plentiful dark matter is compared to visible matter. These methods of cluster analysis include analysing the scatter in radial velocities of the galaxies within the clusters, analysing the frequency and intensity of X-rays emitted by hot gases within the clusters, and the third method is also the third line of proof, analysing gravitational lensing. Gravitational lensing occurs, from our perspective, when travelling light photons are slightly bent and warped on their path towards Earth by the gravity field of a massive object or structure in between the light source and us, causing a lens-like light formation when it reaches us. By measuring the bend of the light, it is possible to deduce the mass of the object that the light is circumnavigating, usually a galaxy or galaxy cluster. This gives us a good estimation of the disparity between the visible mass and the actual mass of a galaxy, and as such tells us how much dark matter is within it. But dark matter can also take gravitational lensing a step further all by itself. Lensing occurs around swathes of dark matter too. While it doesn't seem to interact with normal baryonic matter or light, light interacts with the gravity field of dark matter, and we can observe the resulting effects and analyse the light warp to deduce the mass of the dark matter in its path. The big indicator that the source of this mass is dark matter is that we have observed lensing occurring with no obvious source of gravity, and principally no visible matter. Light just appears to be warped as it travels through empty space, but this cannot be the case. So we now know that there must be something with mass in that area that just doesn't emit or reflect light. All 3 lines of evidence tend to agree that dark matter outweighs visible matter at a ratio of about 5 to 1, and this is where the statistic that dark matter accounts for between 80 to 85% of the matter of the observable universe.
Doesn't make any sense though.
The search for this abundant subatomic particle underpins one of physics' greatest initiatives, and with its existence all but confirmed, how close are we to finding it? If dark matter is indeed an undiscovered particle, then if we can isolate it and comprehend its properties and behaviour in a lab, then perhaps we can find uses for it, and perhaps we could tailor its use to improve technology here on Earth. We've been hunting it for decades, but we still haven't managed to isolate it yet. We've employed a few different strategies, such as trying to recreate it in the Large Hadron Collider, but so far we've come up empty. However, it is important to remember that scientific breakthroughs are more mobile than ever these days thanks to advancements in technology. We've just photographed a black hole, something that was thought impossible 20 years ago. Furthermore, AI and machine learning are helping us to refine our search techniques to elevated levels of perceptivity. All we need is one stroke of luck, and it's likely that we will have found or isolated dark matter within the next decade. So who knows? Maybe some of you watching this video right now are watching at a time when the search for dark matter is complete. After all, I made a video that highlighted the uncertainty of black holes a mere 2 days before the black hole photograph was released. So to summarise, dark matter is most likely a form of undiscovered particle that is abundant in galaxies and galaxy clusters. Its abundance results in its mass vastly outweighing the mass of ordinary matter, but we didn't know this until recently because it doesn't interact with baryonic matter and doesn't emit or reflect light, and so is invisible to all our instruments and observations. However, we can use clever methods such as the reverse engineering of its effects on gravitational lensing to deduce just how much mass it accounts for, and with all things considered, we are now on the path to isolating it in the lab. Until that day comes though, we do truly remain in the dark. The full story of dark matter is a work in progress, and in the meantime, we are scouring the cosmos and smashing particles together in an attempt to better understand this phenomenon. It's pretty cool. Despite never having found the actual particle, we understand dark matter very well. So what about dark energy? Well, this is a much different story. Dark energy is very different to dark matter despite the name. Whereas matter is something physical that follows a constant law, energy is a quantitative property of the universe. This kind of energy, however, has an added layer of mystery and impossibility. Dark energy is an unknown form of energy that is hypothesized to be present in all parts of space and time, right across the known universe and beyond the cosmic horizon. It is sometimes referred to as vacuum energy for its presence in the near vacuum of space. Dark energy is suspected to contribute about 2/3 of the total energy density of the currently observable universe. Earlier we addressed that dark matter accounts for about 1/4. While it accounts for most of the mass in the universe, dark energy doesn't have a mass, but it still vastly outweighs dark matter's share of energy density, and this figure is about 27%. Dark energy makes up 68%, and the rest, the normal baryonic matter and energy in atoms, makes up a measly 5%. These figures have well-defined error bars and may vary following the making of this video, but whatever the case, just know that normal matter is dwarfed by dark matter, and dark matter is dwarfed by dark energy. There are two proposed forms for dark energy. The first is the cosmological constant, proposed by Albert Einstein, supposing a constant energy permeating throughout space homogeneously. The second is through scalar field theories, suggesting dynamic amounts of dark energy throughout space, varying based on its surroundings. If that was hard to understand, it basically means that dark energy is either consistent everywhere in the universe, or it may vary in quantities depending on its surroundings like dark matter does. It is, in all likelihood, constant throughout the universe, meaning it is as present here on Earth as it is in the farthest corners of creation. But despite this apparent volume of dark energy, it is estimated to be very low density, much less than ordinary matter and dark matter. However, it is the prevailing energy in the universe because, whether it is constant or varying, it is believed to be present across all of space. Whereas dark matter varies and is more prevalent in galaxies and structures, dark energy is everywhere. Dark energy represents a negative value in Einstein's cosmological constant. It doesn't deteriorate or spread out as the universe expands, but instead appears to increase. The more space grows, the more dark energy there seems to be. It completely breaks the laws of normal energy and truly numbs the mind. I guess you could say a more appropriate name could be paradox energy. Like dark matter, dark energy hypotheses arose due to mathematical shortcomings. The cosmological constant was proposed by Einstein when he released his field equations.
What if dark matter just doesn't exist at all? And it's just someone who messed up their math. That'd be kind of funny.
The static universe. Dark energy was used in this equation to balance gravity, but then the static universe model was disproven in the 1920s when Edwin Hubble discovered that the universe was actually expanding. Einstein referred to the cosmological constant and static universe as his biggest blunder. It wasn't until the 1980s that two scientists, Alan Guth and Alexei Starobinsky, theorized that a negative pressure field, similar in nature to what we now understand to be dark energy, could have been responsible for cosmic inflation. This was an event that occurred a fraction of a second after the Big Bang, in which a highly repulsive force dramatically and exponentially elongated and expanded the universe, flinging matter out quickly and in every direction. It's not clear what links dark energy and cosmic inflation, but our understanding of the latter helped us to refine our theories, and some new dark energy hypotheses began emerging in the following decades. In the 1990s, the universe was believed to be on the path to an ending known as the Big Crunch. It was believed that the gravity of large objects within the universe would slow its expansion to the point that it began to recede, and this was somewhat on the money until about 5 billion years ago, when everything appeared to change. The High Z supernova search team then began analysing the expansion of the universe to determine its shelf life, but what they actually discovered was something far more terrifying. When they analysed distant supernovae, They realised that the more distant objects seemed to be much further away than expected for a consistently expanding universe, and as such, they stumbled upon the discovery that the universe is not only expanding, but that its expansion is also accelerating. Dark energy is the accepted model to explain this finding. The team found that by comparing distances in relation to redshift, the universe had expanded more in the latter half of its life, coining the dark energy dominated era. This is because the universe is expanding everywhere, in all parts of space, and it's not a sphere expanding uniformly. Empty space is elongated in every direction at a rate of about 68 kilometers per second per megaparsec, and so the larger the universe gets, the more interior there is that is expanding too. The more volume there is inside the universe, the more volume there is that will grow, and it's a scarily exponential process, hence why the vast majority of this growth has happened in the latter half of the universe's life. This is why the universe appears to be expanding faster than light relative to us at far enough distances. Dark energy permeating all of time and space is the catalyst for every point in space to be expanding and far across the universe after so many megaparsecs. This compound growth reaches an apparent speed relative to us that is faster than light. This doesn't break the laws of special relativity, however, as the speed of light is
basically
only a constant speed for transferring
they're going away.
If two objects move away from each other,
so I can understand it there. 2 points here. They're going away. This one's going like half. Like here, down here. Right. Two galaxies. This one's going at 3/4 the speed of light. This one's going at half. Right now they're going 1.25 speed of light away. But then one's not going faster than light. But they're relative. They're going, the distance they're going away is faster. So
at 51% the speed of light each, they would appear to be moving away from each other faster than light.
Yeah.
Obviously, the universe's expansion is a lot more complicated, but that is the general idea. Faster than light recession is only apparent due to the apparent speed of two contrasting points of intergalactic space. After this, the lambda CDM model became the front-running model for dark energy and the universe's expansion, and follow-up observations in the early 2000s lent credence to dark energy's existence and role in this process. The term was coined after it was adapted from dark matter, and the previously dismissed cosmological constant actually turned out to be one of Einstein's more rigorous and impactful equations, as opposed to what he perceived to be his greatest error. Dark energy is predominantly evidenced by the need for an additional type of energy as a catalyst for the universe's accelerating expansion. There are many complicated observations around supernovae and cold spots in the cosmic microwave background to evidence dark energy's existence, but because of its nature, we can't really get much closer than that. But what is its nature? Well, why it exists and how it works verges more on the unanswerable questions of creation, but what we do know is that it represents a negative value in Einstein's constant, as mentioned. Simply put, the more space expands, the more dark energy there is. More dark energy appears with the space existing dark energy creates, and this process continues exponentially. We don't know how or why, but there have been a few hypotheses. The simplest explanation would be that vacuum energy could just be a
I love how listening to C is just so much better than, like, you know, school.
Then perhaps it is just an inevitable feature of the fabric of the universe. This could explain why dark energy is increasing. If it is a naturally occurring byproduct of the interior of the universe, then it wouldn't really require a source of energy on the inside per se. However, when we attempted to test this hypothesis, the results were wildly inaccurate and not in line with the exhibited behaviour of the universe. In the wake of this disparity, an alternate hypothesis is that dark energy could be the result of temporary virtual particle pairs and their interactions. Quantum field theories detail what are known as vacuum fluctuations, driven by
And we have it.
uncertainty.
In the 3 hours that I've streamed,
means that random pairs of virtual particles appear all the time.
we have
latch
finished
onto one another,
this much,
destroying themselves in the process. The resulting latch creates energy.
including one missing piece.
Interactions
So
occur in unfathomably quick succession.
Yep.
And the energy generated will be incredibly
that's gonna be it for the stream today.
Over the vastness of space, these tiny
Yeah, I think that's gonna be it. Say goodbye if you want. I'm going to go set this on the floor and end the stream.
if that's it, I'm going to put my desk back in order. And then so permit. That'll do for now. So I guess that's it for this room. Bye.